Hello everyone, my name is Bohlender. I'm from the Knowledge Engineering group at TU Darmstadt, and this is our paper Extreme Gradient Boosted Multilabel Trees for Dynamic Classifier Chains. I'd like to start with a small introduction to multilabel classification. In contrast to binary classification, where there's only one class, which can either be set or not set to an instance, we now deal with a large set of different class labels, and each instance can be assigned to multiple of these labels. Each label is hereby represented as a binary value, where 1 means the label is assigned to an instance, and 0 means the label is not assigned to the instance. I have provided a small example with movies, so you can see we have features like year, title, actors, and summary, and our labels are just text which have to be assigned to this movie. So for example, Harry Potter is a fantasy family movie, Mission Impossible is an action movie, Star Trek is a sci-fi and action movie. Let's continue with our motivation for a dynamic chain approach. Therefore, we take a look at a traditional model, the classifier chains. This is basically a chain of classifiers. On the right hand side you can see how this works. So the first model takes as inputs the original features from our dataset and has a task to predict only a single label, so this is a binary classifier. The next classifier also uses the default features, but adds the predictions of the previous classifier also as features, with the task to predict the next label. And this step continues until all labels have been predicted. Where this classifier chain approach predicts labels in a static order, and the advantage is that these subsequent classifiers can use predictions of the previous classifiers as input features, and this allows the classifier chains to consider static dependencies between these labels. However, these classifier chains have some problems. So the first one is that their predictive performance depends on the chain order, so the order in which we predict the labels, and local dependencies may require different chains. I have given an example for this problem in an image classification scenario. So now we want to find cars and their headlights. On a daytime image it's easy, we at first find the car, and given the car we can find the lights. But if we use the same order at night, where we also want to find at first the car, this is harder and may result in this wrong rectangle. Now, given this rectangle, predicting the lights may also result in a wrong prediction. So the idea is to don't use this order, but use an individual order. And in this image, it's much easier to at first detect lights, and based on these lights, find the car. And this is also the idea of our dynamic chain. Our dynamic chain can predict labels in individual order per instance, so we have exactly these two correct examples. And we predict labels with high certainties at first. Now let's take a look at the base models we use inside our dynamic classifier chain. These are XGBoost models. We use them because they are good known for their predictive performance, but had to make some modifications to allow for multi-label classification. On the right hand side you can see the typical structure of such a decision tree, and the main difference is that in the binary setting there is only one value in each leaf that represents if an instance belongs to a class or not, and in the multi-label setting we have a vector that has a score for each individual label. Now if we have a look at the tree construction, there were also some modifications needed. So basically the tree is constructed by evaluating different feature splits in each node. These are evaluated by a so-called gain function that is based on gradients and Hessians of the loss function, but I don't want to go too much into details here. The traditional gain is calculated like this. So we have the gradients g, the Hessians h, and the regularization term epsilon. For our multi-label version, we now propose different gain functions, a so-called sum version, where our goal is to find a split that is good for all labels, so maximize the purity for all labels. This is done by just summing up the traditional gain function. Our second version is the so-called max version. It has the goal to find a split which is the best for a single label. This is good because in each round of our chain we also only predict a single label. Then we have some specialized versions. these focus only on positive labels. As you can see, the previously two versions use the gradients in a squared form. This means we can't differ positive and negative labels. So instead of squaring, we only use the gradient here minus the gradient, again in the sum and maximum form. These models are a fundamental part of our dynamic classifier chain. We start here with the predicting process. So our initial element is a dataset, where X represents all the given features, and we have added 3 extra feature columns, which are initialized as unknown for each of our 3 labels. Then we use this previously trained model to generate predictions for all our labels and propagate these to a new version of the dataset. The propagation here is that we only propagate one label per instance, and the idea is to propagate the one with the highest probability. These are marked in green, or if there is no label with a probability above 0.5, we propagate the one with the lowest probability, which can then be seen as a negative label. So this is a result after the first step, and we use this updated table in the second step to use the second model, which then predicts with this dataset where we have some initialized label features and have this new prediction. Again, we propagate only one label. As you can see, 0.52 is not propagated because it was set by the previous model, and also 0.51 is not propagated since here we have already a propagated negative label from the previous round. The last step is then to replace all missing values with negative labels since no positive ones have been predicted for these instances. The training process is quite similar. Again, we have our dataset where we have added the feature label columns, but before any predicting, we use this empty dataset to train new XGBoost multilabel model. After this is done, we actually use this model to generate the first round of predictions, which you can see here. And same as before, we propagate one label per instance to create an updated version of our dataset. This dataset is then taken in the second step, and we train a new model based on this updated version. This can repeat until we have trained the full chain or some other criterion for stopping is met. However, after the first experiments, we came up with some problems that required further refinements to our model. The first problem was that consecutive chain models tend to learn the same trees. The reason here is that during the tree construction, always these splits were chosen where one label was maximized. Now, even if this label has been already set by a previous classifier, the same tree was learned again. So our solution is to exclude these already predicted labels from the tree split evaluation to motivate it to find new splits where other labels are maximized. A second problem was that our final predictions contained way too little positive labels. Our solution to this was to fill unset labels at the end of the chain with predictions from previous classifiers. So the idea is basically, if this is the outcome of the chain, we merge it with all predictions from previous rounds, only the positive predictions, and get this updated version here, where you can see the number of unset labels is much lower. And again, same as before, the final predictions are generated by replacing these missing values with 0. Now we come to our experiments. We have evaluated our model on 11 different datasets from different domains with different numbers of instances, labels, and cardinalities. The models we have used as baselines are a binary relevance model. This just learns a binary classifier for each label. In this case, we use XGBoost models. Then our classifier chains we have seen previously, also using binary XGBoost models. A dynamic classifier chain with random decision trees. And our dynamic chain models, so XDCC STD and XDCC con for the standard version and the cumulated version. And the last model is an ML XGB model. This is just our chain with length of 1, or basically just one single multilabel tree model. So at first we take a look at our prediction development. Therefore we have plotted the handling accuracy and training times of the classifier chain, represented by these two horizontal lines, and our dynamic classifier chain, represented by the dotted lines. The red ones represent the training times. The dotted and dashed line represents our standard version, and our dotted solid line on top represents our accumulated version. There are some observations we can make. At first one is that the dynamic classifier chain score improves with more previous predictions available. This shows that the model is somehow able to use these previous predictions to improve. The second observation is that there are only minor improvements after chain length of 4. The reason here is that the cardinality of this dataset was about 4, so all or most of the relevant labels should be set by round 4. Also, we can see the dynamic chain training is faster than the classifier chain training. The reason here is that our models are smaller, and through our separate and conquer approach, the number of labels to evaluate during each tree construction step also reduces. The last observation we can make here is that the accumulated version is much better than the standard version, and this is mostly so for all our datasets. Next, we take a look at the training times. Therefore, we have plotted the training time ratios between the accumulated version of our dynamic chain and the classifier chains in relation to their F1 ratio. What we can see here is that each point on a line represents one round of the dynamic classifier chain. And if this is below 1.0 on the x-axis, it means that the chain up until then is faster to train than the default classifier chain. We can draw two conclusions from this plot. So the first thing is that our dynamic models only improve in the first few rounds. So yeast, for example, converges up until point 4 or 5, whereas BibTeX, because of its dataset size, takes a bit longer. It needs about 20 to 30 rounds until convergence. And afterwards, there are only minor improvements. This also means that training a model until its convergence point is always faster than the classifier chain model, where we end up at BibTeX at 0.8 and all the other models way before this point. This also allows us to reduce our chain length during training. Already a reduced chain is able to provide good results, which would otherwise only minor improve if the chain would be longer. The last thing we want to show is the actual predictive performance of our models. Therefore, we have created this table that shows the average ranks over 10 datasets for handling accuracy, subset accuracy, F1 measure, and the actual training times. And what we can see here is that binary relevance is a really strong baseline for handling accuracy. This is here the leading score, whereas the classifier chains are really strong for subset accuracy. Our dynamic classifier chain models are a bit of a trade-off between both of these measures, which can be also seen in the F1 score where we are leading here. Our last observation can be found in the training times, where we can see that both of our models are faster than the traditional binary relevance and classifier chain model, and as expected, the single multi-label model is here the fastest. This takes us to our conclusion. We have proposed a new approach for a chain of classifiers to predict labels in a dynamic order and adapt to each instance individually. We have also proposed an extension to the extreme gradient boosted tree algorithm that allows multi-label classification, which is not possible in the default version. This brings some advantages. So the first thing is we can really predict labels dynamically for each instance and are not forced to predict the same one for all instances. Our maximum performance is already reached after a few rounds, which allows to train chains which are shorter than the number of labels. And this results in a substantial improvements regarding computational costs. That leads me to the end of my presentation, and thank you for your attention.